Let's talk about transition metals in ionic formulas. So the transition metals are the elements in this part of the periodic table here. And when we write formulas for ionic compounds that contain transition metals, the formulas look like this, with these Roman numerals here in the middle. So this might be a little bit different from other types of chemical formulas you've seen. So in this video, we'll talk about what's going on here. Okay, so transition metals. As I said before, the transition metals are the elements in this area here of the periodic table. I've written some of the most common ones in. Now, I'm also going to be talking about some of the metals over here. Okay, these guys here aren't technically transition metals, but they act a lot like the transition metals in certain ways. So I'm going to be including them in the discussion as well. Now, for ionic bonding and ionic formulas, transition metals are a little bit different from the elements here and here on the periodic table. This is the reason why. Transition metal elements, or at least I should say many of the transition metal elements, are able to make more than one type of ion. And each one of these types of ions has a different charge. Let me show you what I mean by this. Let's start by taking an example that's not a transition metal. We'll take lithium in this column here. Okay, so lithium. When lithium forms an ion, we know that that ion is going to have a +1 charge, and that's because lithium is in this column. Every single ion that lithium makes is always going to be +1. We know that based on its location. Now, the same is true for calcium. Okay, calcium is in this column here. So when calcium makes an ion, that ion will be Ca2+, and it will always, calcium will always make ions that are 2+. Every single calcium ion, for the most part, will be Ca2+. Now, on the other hand, transition metals are a little bit more loosey-goosey about things, okay? Iron, Fe for example. Iron can make an ion that's 2+, but it can also make an ion that has a 3+ charge. So it's able to make both these types of ions. Gold, which is another transition metal right here, can make Au1+ with a 1+ charge, or it can make a type of ion that's Au3+. Manganese, which is right here, is one of the craziest of the transition metals because of the huge variety of ions that it can make, okay? A manganese element can turn into Mn2+, or Mn3+, or Mn4+, or Mn6+, or Mn7+. So the point is, the transition metals can make multiple types of ions, and these ions all have different charges. This is different from the metals over here and from other types of elements on the periodic table, which tend to always make the same type of element based on what column they're in. Now, sometimes people ask, why is it that the transition metals are able to make this wide variety of ions? And the answer is kind of complicated, but basically it has to do with the way electrons are arranged in the orbitals of the transition metals. Essentially, the transition metals are more loosey-goosey with the electrons that they give away. They're not set on giving just one away or two away. They can give a couple away, they can give a couple more away, and so that's how you end up with these ions that have varying numbers, varying amounts of positive charge. So, when we have these elements that can make different types of ions, how do we tell them apart? Well, we have to use a naming system that uses Roman numerals. I'll show you what I mean. So using this Roman numeral notation, we call the Fe2+ ion, we call that iron 2, with a 2 in Roman numerals in parentheses. Iron 3+ is iron 3. Gold 1+ is gold 1. And manganese, for example, 4+, 6+, 7+, are written as manganese 4, manganese 6, and manganese 7. Now, you might be a little bit unfamiliar with how to write numbers in Roman numerals, so it probably wouldn't hurt to do a real quick review of Roman numerals before we move on. So here's how to write the numbers 1 through 10 in Roman numerals, okay? 1, 2, 3 are pretty straightforward. Then 5 is a V and 4 is an IV because it's 5 minus 1. If a number is to the left, it's subtracted. So 1, 2, 3, 5 minus 1 is 4 and 5. Then we have 6 VI, 7 VII, 8 V with 3 I's, and then we have the same thing with 9. 10 is an X, and 9 is an X minus 1. Now, it's very unlikely that you would run into an ion that had a charge of 8, 9, or 10, but hey, this might just be useful to keep in mind anyway. Nonetheless, 4, 5, and 6 tend to be quite common ionic charges, so you want to be sure to know how to write these numbers in Roman numerals. So we're going to use this Roman numeral notation whenever we write formulas with transition metals, because we have to explicitly say what charge the metal has, because we can't just figure it out based on where it is on the periodic table. So we have to say manganese 2 chloride for a compound that contains Mn2+. For iron 3 oxide, we write that so that whoever's reading it knows that we're talking about a compound that contains iron with a 3+ charge, okay? This Roman numeral notation is different from formulas without transition metals, where we just write calcium fluoride, or we'd write sodium sulfide. We don't have to use Roman numerals when we write formulas without transition metals because it's totally clear what these charges are, right? Calcium is in this column here, so we know for sure that it's 2+, and it's always going to be 2+. Sodium is in this column here, so that we know that it's 1+, and it's always going to be 1+. So we don't have to use Roman numerals when we write formulas without transition metals, and in fact, it would be wrong to use Roman numerals when you're doing this. So don't put Roman numerals into the formulas unless they have transition metals. So that's an introduction to transition metals in ionic compounds. We saw how one transition metal element can make multiple ions with different charges. In the next 2 videos, we're going to learn how to take the name of a transition metal compound and write a formula for it, and then take a formula and name it. Writing formulas is pretty straightforward because the name gives you the charge. On the other hand, though, taking a formula with a transition metal element in it and figuring out what the name is, that can be a little bit more challenging because you've got to figure out what the charge on the metal is, and it's not clear right away from the formula. So we'll look at how to figure this out using some math. Check out those next 2 videos called Writing Formulas for Compounds with Transition Metals and Naming Compounds with Transition Metals.